Hello, my name is Rob Reynolds. Welcome to Calculus, Business Calculus, Section 1.2. Today we're going to look more in depth at functions, graphs, and even introduce the calculus topic of limits. So the first thing we need to know is just a little bit about what functions look like and the library of functions, which sometimes we can play these Simon Says games. So I think I did this a little bit yesterday, but you should know this is a line. This is a parabola. You should just know the general shape, an S shape here, a W or a U. Now x to the 6 would be the same. X to the any even would be the same. This would be x to the odd. I'll say the first and the third quadrant are ending behaviors, and if it's even, it would be the first and the second would be the ending. Ending behaviors just means it goes to infinity in those quadrants. This is the absolute value. It's a V-shaped value. You can remember that. Square root function over 1 up 1 over 4 up 2, because the square root of 4 is 2, so there's a 0.4 comma 2. The cube root function, it looks like the square root function. It's not exactly, because the cube root of 8 is 2, so it's over 8 up 2 opposed to over 4 up 2. But it also goes the opposite direction, because you can take the cube root of negative 8 as well. So the cube root of 8 is 2. The cube root of negative 8 is negative 2. You should know the reciprocal function, hyperbolas. You should know exponential functions, and you should know logarithmic functions. And if an exponent function goes through 0, 1, logs are just the inverse. Every time you see an x, write a y. Every time you see a y, write an x. So 0, 1 becomes 1, 0. So sometimes we call a constant function, like if it's just like y equals 5. 5 is a constant. Then it's just a horizontal line, and it looks like this. So it's constant. The y value is constantly the same value. The identity function means every time you see an x, it also equals the y. And so if you know the form y equals mx plus b, where the slope is 1 and the y-intercept is 0, you recognize this as just a straight line, 45-degree angle. The square function, y equals x squared. Sorry about that. We already talked about what that looks like. It's a parabola shape. The cubic function, again, you kind of should be able to recognize what that looks like before I reveal it. Again, you can plot some points, but I'm not interested in you plugging in for x and solving for y right now. I just want you to know the general shape of a square root function. And the value of this is, if you type this in the calculator and it's wrong, you should have some kind of sense of, oh, well, that's not the square root function. Square root functions look like this. And it doesn't really matter if it's y is equal to 3, the square root of x plus 4 plus 5. We're going to learn that this just shifts 4 units to the left. This shifts 5 units up. And this is called a vertical stretch. So that's actually like a rubber band, just kind of stretching it up higher. But no matter where it's shifted, again, it could go to the left and it could go up. But no matter where it's shifted, it still looks like a square root function. It may not start at the origin. The cube root function, again, you should kind of have some semblance of what that looks like. Kind of like walk like an Egyptian, kind of heads off this direction in both directions. The reciprocal function is what kind of an elephant? Elephant is that with a beak? I don't know. Odd, strange. So this is the the reciprocal function. Sometimes we call it a hyperbola. The absolute value function looks like a V for victory, beat Valley. My wife teaches at Valley High School, but I taught at Dowling, so rival schools. Oops, just already talked about this one. Looks like that's a repeater, 1 over x. And the greatest integer function is something I haven't mentioned. Greatest integer function is the greatest integer less than or equal to x. So for example, if I were to do a t-chart, which I'm not a big fan of t-charts, but sometimes they're helpful. If you let x be 1, the greatest integer less than or equal to 1 is 1. If you let x be 1.1, the greatest integer less than or equal to 1.1 is still just 1. And 1.9, yes, it rounds to 2, but the greatest integer less than or equal to 1.9 is still just 1. Sometimes this is referred to the step function. because when all said and done, it kind of looks like a staircase or a step. So you can see 0.5, the greatest integer less than or equal to 0.5 is 0. 0 is an integer. And this is 1.5, and the greatest integer less than 1.5 is y is 1. So if you let x be, well, what's this, 4.5? If you go over 4.5, you're going to go up to only 4 because the greatest integer less than or equal to 4.5 is just 4. And you could do the same thing with the negatives. So your calculator will do the steps. You can graph these functions. Turn off your plotter if it's on. That might have been the last thing that we did. So just highlight it and press enter. Come back down. The greatest integer function is under math, num. Well, there's the absolute value, but greatest integer is number 5. So either you could just scroll down to number 5, or I just like to hit the number 5. And then x is next to alpha or below mode is your X key, and I'm going to hit zoom 6. That'll give me a standard 10 by 10 by 10 graph. Again, the open and closed dots don't show up, but you can see if I hit trace and 0.5, then sure enough, I get the greatest integer less than or equal to 0.5 is 0, and you could type in 1.2. The greatest integer less than or equal to 1.2 should be a 1. And so you can't see open and closed dots like this graph, but certainly your calculator will graph this, as well as all of those. So you can use your graphing calculator. I think you're supposed to, on your handout, if you went to Blackboard, here's some graphs that you were supposed to kind of label and sketch along. So you should be able to recognize these graphs. Not only should you be able to recognize them, I would expect you to be able to sketch them and then kind of identify x and y intercepts. To find an x-intercept, you let y be 0, and to find a y-intercept, you let x be 0. So sometimes we just make a quick t-chart like that and find x and y-intercepts. That's a quick way to find 2 points on the function. You should be able to write standard forms of circles, which is what, x squared plus y squared is equal to r squared. Kind of looks like what we learned in section 1.1, the Pythagorean theorem, a squared plus b squared equals c squared, which is also the distance formula. X minus x quantity squared plus y minus y quantity squared. So they're all in the same family. And it kind of makes sense that circles has something to do with distance, because the definition of a circle is all the set of points that are equal distance away from the center point. So if the distance is r, you can see that I'm replacing r with the distance formula and just taking the square root of both sides. Finding the points of intersection between two graphs, we just set y sub 1 equal to y sub 2. We can even do that on the calculator. I'll show you how to do that in a moment. And then the purpose of this class is to give you some real life applications, business applications, where you might use this in your economics, if you're an economics major, or what kind of a business major you are, finance. Hopefully there's some practical applications for this. They're making you take the class, so I would expect there to be some practical application. This is the formula for the relationship between converting from Fahrenheit to Celsius, and of course I could give you a formula from Celsius to Fahrenheit as well. But you should feel comfortable sketching a graph, and the book says go ahead and just plug in for x and solve for y, and again making t-charts. I'm not a big fan of that. I would not encourage you to plot points. I would encourage you to look at the form y equals mx plus b, where you know that the slope is the negative 3 over 1, which is the rise, whoops, how do you spell rise? Over run. And then this b is called a y-intercept, and that's a start value. So you go to the y-axis and find 1, 2, 3, 4, 5, 6, 7. That's a start value. So it's called the y-intercept, or a start value. That's where you start graphing the line, because you can't do the slope until you have a point. So from that point, I'm going to do my slope, which is rise down 3. So 1, 2, 3, and run 1. And I could do that slope over and over again, down 3 over 1. And I could fill out the chart and make a nice straight line. I think that's more efficient than plugging in for x and solving for y. Learn how to graph lines using slope and y-intercept. This slide is demonstrating if you let x be 0, this is a y would equal 7. So just plugging in for x and solving for y. But again, here's the final solution. For graphing this line, you should know that it's a line before we started graphing, because it was x to the first, and anything that says y equals x graphs some kind of a line. Maybe you recognize this as your slope, which is negative, and you read a line like you read a book from left to right, and by moving from left to right, that's going down or in the negative direction. Here's another equation of a line, because it's y equals x to the first. but I'm going to teach you monkeys wouldn't prefer apples over bananas. Most teachers teach you to solve for y and put it back into y equals mx plus b form. I'm not going to do that. I'm not going to do the t-chart, which is plugging in for x and solving for y, although you could find x and y intercepts pretty easily here. But I think the easiest way to do this, well, let's start this by x and y intercepts and show you why I'm not the biggest fan of x and y intercepts. To find an x-intercept, you let y be 0. To find a y-intercept, you let x be 0. So if we let y be 0, that'll wipe this term out, because 5 times 0 is just 0, and then divide both sides by 4, and I will get the answer. I'm going to back up here so I can undo a little bit of what I just did there. The 16 divided by 4, if I let y be 0, is 4. But if you let the x be 0, again, that'll wipe this term out, and I get 16/5, which is very difficult to plot. In fact, I would encourage you not even to try. So this little guy reminds me of monkeys wouldn't prefer, apples wouldn't prefer, that's the negative, apples over bananas. So if you know the standard form ax plus by is equal to c, you can do monkeys wouldn't prefer the opposite of this number, which is -4, over this number, which is 5. That's a positive 5. So the opposite of the a divided by the b gives me the slope. And once I have 1 point, which I do, 4, 0, which means go 1, 2, 3, 4 to the right, and no units up, then I can perform my slope. So it's easy to find slope for the equation of a line given in standard form, which is this ax plus by is equal to c. All you have to do is find one nice point, which we did. That's called the x-intercept. And then let's do the slope, down 4, and run 2, 3, 4, 5 to the right. And of course, instead of going down and to the right, you could go 1, 2, 3, 4, and 1, 2, 3, 4, 5 to the left, because that's the same thing as 4 over -5, which we never write it like that, but that's what I did. I did the rise, and then I ran to the left. And that's the only time that you run to the left. I usually say, this is Reynolds' world. You always put the negative up top, so that means you're always running to the right. But you can see that creates a nice straight line. I might consider doing that slope one more time. The book or the author is going to encourage you to plug in for x and solve for y. Again, that's probably my least favorite way to do this. I would recognize this as an x squared function, and it's simply shoved down 2 units. And all x squared functions, well, parent graph of the x squared function looks like this. It's over 1 up 1, over 2 up 4, over 4 up 16. I could go and find many points, but it starts at 0, 0. But now this says go down 2 units. So I take that 0, 0 and shove it down 2 units. And then I do the value of a again, which is over 1 up 1 over 2, because 2 squared is 1, 2, 3, 4. And so I can see that I have nice little symmetry going on here, over 1 up 1, over 2, 1, 2, 3, 4. And there's a nice parabola. That beats plugging in for x and solving for y every day. You're certainly welcome to plug in for x and solve for y. That's not what I'm trying to teach you. What I'm trying to teach you is, hey, I recognize this as a parabola because it looks like y equals x squared. It's simply just shoved 3 units to the right, 4 units up, and I'm going to talk to you about this. It's called a vertical stretch. It's kind of like a rubber band. So instead of it going over 1 up 1, which I normally do, over 1 up 1, this has a vertical stretch of 2. So it's going to start here. Actually, it doesn't start at the origin because it goes 3 right and 4 up. I'll talk to you about it in a minute. But the vertical stretch, if it says y is equal to 2x squared, you go over 1 and up 2. And that's like that rubber band that's stretching it forward. So over 1, up 2. And it's always over 1 and then up whatever the a value is. In this case, the a value is 2. What am I talking about with the a? Well, in the general form, we call a that vertical stretch h quantity squared plus k, where h and k is the vertex. That's called the starting point or the turning point. So I'd like to start 3 units to the right, 4 units up, and then from that point, we just go over 1 up a. So over 1 up 2 on both sides, over 1 up 2, and there's a pretty good graph. 3 points determine the parabola. If you wanted to plot more, you could, but that gives me a general idea of what that looks like. That would be the process that I would look for. If it's given in this form, which is a standard form, it's not the graphing form, because the graphing form would be what I just gave to you before, y is equal to x minus h quantity squared plus k. where you can see it's still an x squared function, but this is just written in a delivered form. We could complete the square. I think that's in some section here coming up. But we could also graph this by x and y intercepts. So this has one y-intercept, and this has 3 x-intercepts and then 1 y-intercept. And keep in mind, if the x-intercept is 0, 0, then the y-intercept is 0, 0, 2. You can only have one y-intercept. And the reason why is because if you have more than one y-intercept, then it's no longer a function, because the function has to pass the vertical line test. And if it crosses more than once, it's not even a function. So this is not a function. This is 2 y-intercepts. And a circle, again, it's not a function. It doesn't pass the vertical line test. But this has no x-intercepts. It's possible to have a graph with no x-intercepts or y-intercepts. So again, to find a y-intercept, you let x be 0. To find an x-intercept, you let y be 0. So this just says find the x and y-intercepts. Well, one of the easiest way to do that is just to factor this. If I could pull out an x and factor this to x squared minus 4, and then, we could factor some more. Difference of 2 squares, x plus 2, x minus 2, and then set every factor equal to 0. So x equals 0, x equals negative 2, and x equals 2. And those, I'm done. I did it. Why did I set y equal to 0? Because remember, to find x-intercepts, we let y be 0. So I'm just factoring this thing and setting it equal to 0. You can look at the graph of this thing and determine that it does have x-intercepts. I'll just pull out my calculator here real quick, type in x cubed minus 4x, and hit zoom 6, and you can see those x-intercepts certainly are true. 0, negative 2, and 2. And again, here's just the process of going through. Oh, the author graphed it as well. Circles, we've learned, hopefully you have this memorized, x minus h quantity squared plus y minus k quantity squared is equal to r squared, where h and k is no longer the vertex, but it's called the center of the circle, and r is the radius, distance from the center. So here's the general formula of a circle. Now remember, h and k is at the center, then it becomes a lot more simple. A form of a circle, which I think I showed you earlier in the video. And again, r is not the diameter, but it's the distance from the center to any point on the circle. So standard form, and again, this form is if h and k is at the origin. So here it goes. Since this point lies on the circle, I will call this as an x and a y. And since they say that the center is at negative 1, 0, I'll call that my h and my k. So when I plug in to x minus h quantity squared plus y minus k quantity squared is equal to r squared, I'll just pick off my x is right here. So 3 minus the h, negative 1, plus the y value, which is 4 minus the 2 quantity squared. I don't know the radius, but I think I could solve for it now. 3 minus 1 is 4 squared is 16, plus 2 squared is 4. That's a whopping 20, but remember you got to take the square root of that thing to find the radius. So to plot it, well, I've got the center at negative 1 and 2. There's the center. Now, the square root of 20 is somewhere between the square root of 16, which is 4, and the square root of 25, which is 5. So somewhere between 4 and 5 is the radius, around 4.5. So you really could just go like 4.5 in all directions. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and a little bit. 1, 2, 3, 4, and a little bit. 1, 2, 3, 4, and a little bit. I'm off, but that kind of gives you a idea of what the circle might look at. And then, well, gosh, I could have just plotted the point 1, 2, 3, and then 1, 2, 3. I'm really close. Look at that. There's that point 3, 4. So again, I was just kind of estimating at that square root of 20, which is close to 4.5, but it may not be exact. But there's a little bit better example of the circle, and then you would plug in and write the final example. Remember, this is x minus h plus y minus k is equal to r squared goes over here. So even though the radius is the square root of 20, the formula doesn't say plug in the square root of 20. It says write it as just the square root of 20 because it's R² over there. So points of intersection, you can literally just set the one function, y sub 1 equal to y sub 2. That's also called a break-even analysis. And in marketing, we're always looking for the break-even point when your profits equal your, or your supply equals your demand, or when you start a business, you want to find break-even points for your sales, your cost, and your profit. Again, the cost is C, the revenue is R. Later we'll learn that the revenue is XP, where X is the quantity and P is the price. So if let's suppose I have a t-shirt company that I'm starting up, and I'm going to sell 20 t-shirts at $5. So 20 times the 5 would be the revenue. That's the money coming in. Don't get that confused with the profit. And P, profit, is a capital P, which is confusing because here was a P, and if I use a small p, that's price. So sorry about the capital P and the small p problem, but profit is really your revenue minus your costs. So don't get that confused with cost. Profit's different than cost. But again, to find a break-even point, I would simply, in this case, they're saying, when does my cost function equal my revenue function? And again, you could do that mathematically by simply setting the two functions equal together. So 0.65x plus 10,000 is equal to 1.2x. I'm going to subtract off 0.65x. It's somewhere around 0.55x is equal to 10,000. And then I would divide through by 0.55. Pulling out my calculator, 10,000 divided by 0.55, not doing that by hand, somewhere around 1818 equals x. And then once I have the x value, I could just plug that in and solve for the y value, or in this case, the revenue. With the error, I didn't have enough zeros in there, so it would have been 10,000 divided by 0.55. So it's 1818, how about 18,182. 18,182 for my x value. Sorry, I didn't put enough zeros in my calculator. But speaking of the calculator, let's go ahead and just see if we can do this real briefly. We'll let my y sub 1 be the first function, which was 0.65x plus the 10,000. Let's see if I can get enough zeros in there this time. And then y sub 2 is 1.2. Zoom 6 just gives me a standard 10 by 10 by 10 screen. It doesn't always find the two functions because 10,000, well, good gravy, 10,000 is like really, really high, and then this is rising and up 0.65 and running 1 unit. So it doesn't surprise me that I can't find it in a 10 by 10 by 10 window. So after Zoom 6 hits Zoom 0, not always a good fix, but at least it finds the functions for you. And then you can see I want to zoom out a little bit further. So I'll zoom 3. I need to see way further to the right. I'm assuming it's intersecting somewhere over this right. So I'm going to hit window and just kind of look at my X max. It's only going up 40. That's my dog. If you can hear him, he's having a dream, evidently. Trace. Oh my goodness. I apologize, but I just noticed I made another typo. I forgot to type in the X value here. So it's not just a horizontal line at 1.2, it actually is increasing, and it wasn't increasing very quickly for me, or if at all. So I'm going to go back to my window and go up 40,000 on the X max and go up 40,000. I don't really care what your Y min is, but we'll hit trace this time, and we finally find a point of intersection here. And to have your calculator find the point of intersection, we'll hit second calculate, and then number 5 is the point of intersection. And this says first curve, we'll just press enter for the first curve. You could be along anywhere you want. On the second curve, just identify the second curve. You might have 3 or 4 curves at a time, so they just want you to identify and then say, what's your guess? And So there's a nice intersection, a quick way to find, well, that wasn't very quick, but if the function's really difficult, this will be a nice quick way. It might have been quicker, obvious, but you can see the y value is what? 21818. It really might have just been much more easy just to take this value and just plug it in there. If I take oh, good grief, that would have been a lot faster. If I just would have taken 1.2 times that, what 18,000, oh my gosh, 182, then there's that y value, 21. And is that the same thing as I had before? Should have been. Yeah, so you can see this y value, 18,182, is this y value. So this y value, 21,800. I guess they didn't find the y value, but I can see that that's really close to the 21,000. So they didn't find the y value like we did on our calculator, but that's one process that you can use for this. The supply equation, supply and demand. The supply curve is a term that you should be familiar with from your economics class. Equilibrium point or the break-even point. Just again, set the two functions equal to each other. When is the supply equal to the demand? Setting the two functions. Example 6, you can try this on your handout. Hopefully you went to Blackboard, and so just I would go to your calculator. I mean, you could do it algebraically as well, but it might be fun for you to practice on your graphing calculators how to just set those two equal. So you could do this algebraically, but you could just let this be your y sub 1 and this be your y sub 2. And I would encourage you to practice that on your calculator. Here's the algebraic way to do that. But again, I would make sure you could do that visually on your calculator to find the equilibrium point. The last thing we're going to look at is how to find the linear regression line or the line of best fit. And here are the directions for it. They're a little bit long. I apologize, but I've typed them all out for you. And I will demonstrate that in a second video, because this video is already 27 minutes long. I'll make a second video for the regression line of best fit, and I'll post that to Blackboard as well. I hope this video was helpful. If you have any questions, feel free to email me. Thanks.